So you had your video class self-study on area in parametric coordinates. So hope that went okay, but this still caused difficulties. So we need to find the area bounded by this curve and this line. And I posted the announcement on Blackboard giving you some clarification on this. It will look, this curve looks like this. It'll look something like this. Okay, and then y equals 17/4 looks like this. So we're really after that area right there. Okay, so what we need first of all is we need to know what's happening there. So what you should have learned in the area idea is that we still approach it the same way we thought about before. Like we think about a typical strip, and easiest in this case would be a vertical typical strip. So what's the area of our typical strip? So back from when we did areas then. So if we thought of this as, say, y1 and y2. Yeah, so the height of this strip is a change in y, right? And it's going to be y2 minus y1. Or the way I wrote it, y1 minus y2. That's the height, and then the width of it is going to be delta x, okay? Okay. So what we saw in the, we just seen in the video is that we still approach area this way. It's just that now we transform this idea. We need to put it into t coordinates. All right. So y1 minus y2 would be, what is y1? Well, y1 is our 17/4, right? And then y2 would be the y coordinate on this, which in terms of t is just given right here. So it'd be minus our t plus 1 over t. So that would be y1 minus y2. y1 being the constant 17/4, y2 in terms of t. So this is what, this is a delta a, right? Delta a of the strip. So we're still doing delta a of the strip. We're just rewriting it the way we did it before in terms of t. So it'd be 17/4 minus t1 plus 1 over t, and then times delta x. Well, x is this, so then we can get dx as so then what dx would be 1 plus 1 over t squared. Then by the chain rule, dt. So delta x would be like 1 plus 1 over t squared delta t. Right, so the negative cancels and yeah, that's right. So that's our typical little bit of area. So we substitute in our y's in terms of t, and then we can figure out what this is like the derivative of x, essentially. The derivative of x, delta x, is going to be the derivative of x with respect to t. And so then our integral will be from, so now we have to figure out we have to figure out starting t value and ending t value. Because we need to add up all these typical strips starting at that, but in terms of t, right? So whatever t1 is, starting there, to t2. So how are we going to find those? So our area is going to be integral from t1 to t2, and then this thing, so higher value of y minus lower value of y times dx, which is going to be derivative of that, dt. So all we have left to do is get the limits of integration. So what are the limits of integration here? How are we going to get those? So we need the t values such that what is true? Yeah, so the y's are the same, right? So it's the t values such that these y1 equals y2. So that means where does 17/4 equal that? So t plus 1 over t has to equal 17/4. Okay, so I'm going to multiply through by, do 3 steps at once. I'm going to multiply through by 4t and subtract 17. So we get 4t squared plus 4t minus 17. So I multiply through by t, I multiply through by 4, and no, that's not right. So this is minus 17t plus 4, sorry. So yeah, so this will be minus 17t plus 4. Okay, and so then we would need, it doesn't look like that factors, so we need quadratic formula. Does it? Maybe it does. Maybe that does. Yeah, that does factor. So we need, yeah, so 4t and 4 and 1. And looks like 4 here, 1 here, minus 17. So it does, yeah. So then we're going to get 1/4 and 4. And when t is 1/4, you get a negative value of, which is going to give you a negative value. Oh, both are positive. 1/4. Okay, yeah. So when t is 1/4, x is negative. So that's this one over here. So we can figure out which one is which by using the x coordinate and seeing which gives the negative x, which gives the positive x. When t is positive 1/4, you get x is less than 0, and when t is 4, you get t2. So this is, so then t1 is the 1/4 from that, and then this one is t equals 4. So we're going to go from 1/4 to 4. Questions on this example? So you got a little algebra to do here. You got 3 terms and 2 terms, so you're going to have 6 terms once you multiply all that out. But then each one is easy in terms of antiderivative, just polynomial-ish, and then take your antiderivative, plug in 4, plug in the 4th, subtract. Questions on this area example? So the area and parametric coordinates is based on the same thing we did before. You're just going to change the variable into t. That means you rewrite your y in terms of t, and you do the derivative of x with respect to t. And that gives you the whole thing in terms of t, and then your limits of integration need to be the, you're still gonna integrate from left to right as it were x, but then you need the t values corresponding to the leftmost x and the rightmost x. Sure they could. But for this area, t is always positive for this area. In fact, I think you get this whole curve with positive t, the way this curve is laid out. This is t values between 0 and 1 give you all negative x values. And then t values greater than 1 give you all x values greater than 0. So for this particular one, you get the whole curve without t being negative. But yes, t can be absolutely negative. I think it's colder in here than it is outside. Is that right? That's crazy. Any other questions about this example? Okay, and so then we're done with parametric functions. So parametric, the area stuff that we did is important for the final. So if you just skimmed that video and you blew this problem off, I encourage you to go back and you got to know that stuff. You got to learn it. But we got to start polar coordinates today, so we don't have time to do it. So that video is important. So if you do need it for the final. Okay. So let me just talk about the Clara project. You also should have seen this explained. So this is thoroughly explained in the video as well, but we'll just make sure we know what we're doing. So that's due Friday. Hopefully you got some start on it there. But this is the idea here, that you've got a silo, and the cow is tethered here at the westernmost point. But the length of the rope is exactly half of the circumference of the silo, so that the cow can make it to the easternmost point. So if the cow were to walk out around and keep the rope taut the whole time, this would be the boundary of where she could graze. So this is the furthest away she can be from the silo as she's walking out away, and so that defines where she can graze, and that would just be half of it, right? So she, or we could say there's a fence here. So if there's a fence here, then that's truly all that she can graze. If there's a fence right here, so that might make it clear. Is there a question? As long as, I think that the worksheet is under the guise that it's all the way around, but as long as you're just going to double whatever you get for the area. So as long as you're just clear on the way that you choose to do it, just say the way that you're doing it, it's the same. It's the same in terms of the work that you have to do. Yeah.
For finding area, do we need to subtract the area of the silo, or are you fine with including?
Okay, so the project is going to be more intensive and more problem solving than just a homework problem. So that's something you're going to have to grapple with. So, but this is a parametric curve, so we got to think about how you're going to find this area, and then also make sure you know there's the example in the video as well of the video that I posted where we talk about area. So, but yeah, it's outside the silo. Maybe that was just your question. Yeah. So there's no pasture inside the silo. It's just outside. So how much grass does she have to graze in outside of the silo? Okay. But in terms of how you're going to get that area of that region, that you're going to grapple with that, and then come get help. Okay. Come get help if you need help. Okay. So, but you need to follow. Follow the instructions very carefully in the sheet as it's laid out. You don't want to go on to the next question unless you're 100% confident on what you've done so far. So don't go on to number 2 until number 1 you're 100% sure. Don't, etc. Number 3 is kind of like, this is the crux of it. Okay, so number 3, this is giving you how you're going to get the parametric equation for that curve. That's the boundary of where she can graze. Okay, so make sure you have number 3 correct. You can consult one of us to make sure. You can also compare what you're seeing on the as a loose check. You can compare what you're seeing on your screen on your TI. to this. If you still have GC, if you had me for Calc 1 and you still have your GC file or GC software, you can put it in on this, and I can help you with that if you need to. So but this visual is also helping you to see that, like I said, like a brief kind of loose check to make sure that you've got those parametric equations right for this purple curve here. So number 3 is like kind of the key part to this whole thing, and then everything else from that is just applying the calculus that we've learned about parametric functions. Okay, so you're going to have to make sense of this geometry here. This is your hint to get that parametric curve. So my experience with this project is that it's difficult, but it's very attainable. If you just need to you just put the time in and work at it, get the support you need, you can do it. Everyone can do it. Okay, and it's really good practice applying all this the calculus of the parametric functions. Okay, 2 pages. Make sure you know there's 2 pages. Okay, any questions? Get started on it soon. You're not going to be able to start this Thursday night and finish it. You're going to need to sit down and work at it, do other stuff, work at it some more, get some help, work at it some more. And that's how you're going to finish it. But you won't finish it sitting down one night and doing it. Okay? What's that? Oh, is that what I said? Oh, yeah, sure, definitely. And how exactly did I frame it? What did I say? That's what I said. A really good job. Oh, professional submission. Yeah, so I guess that's what I meant. So yeah, so so you don't get any. So first of all, to qualify for the extra credit, you have to have the mathematics correct, like at least 95% of this correct. And then if you want to submit in a very, very highly professional way, that's how you would get the extra credits. But you can't just type up and do a beautiful job with mathematics. It's all incorrect. That's not going to earn you any extra credit. Okay. Yeah, you're going to turn this in a hard copy on Friday in class. Okay. Yeah. So I think that's what I meant last semester. I just don't remember. But yes, sure. Pretend you have a job and you're submitting it to your boss. That's professional. Makes sense, right? Okay. All right. Other questions about the Clara project? Cool. Okay, so we gotta move on to polar coordinate systems is our last topic. That's what I thought. Okay. All right, so polar coordinates is a different way of locating points in the plane. So what are you used to? X is the horizontal position of a point, and Y is vertical position, right? So this is a totally different way of locating points in the plane, and that is by, okay, that's okay, just leave it there. So that is by angle swept counterclockwise from 3 o'clock, so that's the standard trig angle. And then distance from the origin, which is called the pole. Okay, so the pole, it's like you're looking down the Earth and you're looking at the North Pole. Okay, so the pole is right here in the middle, and what we used to call the origin is now called the pole. And so you locate a point on the plane by sweeping an angle counterclockwise from horizontal, the standard trig angle, and then based on that, the direction of that, the terminal ray of that angle is the distance called the radial distance, or the distance out from the pole. So let's just an example here. That's there, perfect. Okay, so right there. So there's some angle here, right? Some angle, theta. Okay, and then once that angle is determined, that points out away from the pole in a certain direction, according to that angle theta. The distance that you go out on this black line here then is r. So r is your distance from the pole. And so those two, values of those two quantities represent a unique point in the plane. Sweep an angle, pick a distance out from the pole, and you get this point r theta. So let me pick one where it's actually on an angle that we know here. There, okay. So this is pi over 6. So this is pi over 12. This angle is pi over 12. And then what would you estimate r to be here? This is 1, 2, 3, 4. So r would be something like 3.6. So this would be the point. And r comes first. Although that's a little counterintuitive because really the angle comes first, and then r is determined by the angle, but for whatever reason they put r first in the ordered pairs. So this is the point 3.6 comma pi over 12. Okay, so let's do another one over here. So over here, all right, so notice here, so what's this angle measure? This angle measure is 5 pi over 6. And so say r equals 2. So once you sweep that angle, the terminal ray is pointing in the direction of r. So this right here is not negative 2, it's positive 2. This point is 2 comma 5 pi over 6. So positive values of r point in all directions from the pole, depending on what the angle is. Okay? There is negative r, and that's in the opposite direction from wherever the terminal ray points. Right now the terminal ray is pointing this way. So this point right here on the red ray would be what, about negative 0.7 and 5 pi over 6. So it's still according to the angle 5 pi over 6 with a negative r. So that puts it like back in the reverse direction as the direction for positive r in 5 pi over 6. Does that make sense? So any point can be described with a positive r. Just take the angle. You take your angle to point, and then you go, and the positive direction from the pole is in the direction of the terminal ray of the angle, and then the negative values of r would then be in the opposite direction of the terminal ray. What have I done? Okay, good. All right, so let's just look at a function here. So then what you get is you get r as a function of theta. So given, as you think about angle theta sweeping around counterclockwise, for every value of theta, you get some distance from the pole, and that will give you a locus or a stream of points that create a curve. So here's a function, r is a function of theta, r equals e to the sine theta minus 2 cosine 4 theta. So let's plot that. So you can get an idea of, that's better, okay, let me turn it on. Okay, and so now, so watch what happens. So right now, the angle is 0, but the point is -1. So this would be the point -1, comma, 0 radians. Why? Because at 0, the positive direction of r would be to the right along the x-axis. So negative. So starting at 0 here, it's starting at -1. Okay, so now here is theta changing from 0 to pi over 2. According to that function. So as the angle changed, for every value of angle, you get a different distance from the pole according to that function, and so then you get this loop. Okay, so here's theta increasing from pi over 2 to pi. That's a metric there. And now notice that when we get to pi, the value of r is negative again, right? So at pi, -1 is the value of r, because the direction would be this way, -r would be back this way. And then here's pi to 3 pi over 2, and then 3 pi over 2 to 2 pi. So pretty cool. And you don't get all insect shapes, but this just happens. This particular function, e to the sine theta minus 2 cosine 4 theta, appears like a butterfly. Okay, but this is typical for these functions. You get these you get circles and loops as theta increases. Okay, so that's the idea of r as a function of theta. Distance from the pole as a function of how far you've swept counterclockwise from the positive x-axis. All right, but we got some work to do before we can do stuff like that. So we want to practice plotting. So that was just an overview of polar curves have the function r as a function of theta. Okay, so now what about, it's really important that you're able to transition back and forth between polar coordinates and rectangular coordinates. So let's talk about that. Anyway, there we go. Okay, so this is, I'm showing it here, the angle at pi over 3. And r is, say, 3.4. So this is the point, 3.4, comma, pi over 3. So how would I write the x and y coordinates of that point? Because that point has x and y coordinates as well as, every point in the plane has x and y coordinates. So for this point, pi over 3 and 3.4, what would its x and y coordinates be? Can you figure it out? So let me just highlight this here. So that's the distance from the pole is our r value, 3.4, pi over 3. So how would we get the x and y coordinates of that point? Okay, so you should be thinking trig, right? So this is our standard trig angle, and we have our radius of our circle here. So you should be thinking standard trig here. X coordinate is this right here. Y coordinate is this distance right here. So that's just basic trig. X is 3.4 times cosine of pi over 3, which is 1/2, right? So this is 1.7. And then y is 3.4 sine of pi over 3. Okay, so x then can be expressed as r cosine theta, and y expressed as r sine theta. Okay, this will always be true. This will always be true in terms of given. This is if you had the r and the theta for a point, finding its corresponding x and y. Okay, but these formulas don't supersede common sense. You still leave your brain on when you do these, right? So if I said, and I was looking at the point 5, comma, pi over 2, am I going to plug into these formulas? No, because I know where this point is. Where is this point? 5, comma, pi over 2. On the y-axis, how far up? 5. What's the coordinates of that point? This is not trig, right? This isn't trig now. This is knowing that we're up here at this point right here on the y-axis. It's 5 up from the x-axis, which is the point. See, that has nothing to do with using sine and cosine, right? That's just knowing where this point is and then applying, using your brain, right? Just using your brain. So that's 0, 5. Okay? So, yes, when you have points out here in the quadrants, but when you have points on the axes, you just want to think about it, right? You just want to think about it, and that's better practice of your understanding of polar coordinates than plugging into those formulas. Okay, so then another thing that we can think about is that in polar coordinates, so in rectangular coordinates, there's only one way to represent a particular point. But in polar coordinates, this point, 3.4 pi over 3, there's actually many ways to, in polar coordinates, represent that same point in the plane. Can you think of another way to represent that 3.4 comma pi over 3 to get to that point using a radius and an angle? Okay, so what? Yeah, good. So if I could, we can use negative angles, meaning sweep clockwise. So what angle would that be around this way? Negative what? Negative 5 pi over 6 would be down here. So that would be negative 5 pi over 3. Okay? So then, is it going to be, if I do negative 5 pi over 3, is it going to be positive 3.4 or negative 3.4? So when I do negative 5 pi over 3, my terminal ray is still pointing right here. So I'm going to do positive or negative 3.4? Positive. Okay, so 3.4 comma negative 5 pi over 3 gets me that exact same point that 3.4 positive pi over 3 got. Do you see that? All right, what's another way to get this point? Okay, negative 3.4 and Not because 4 pi over 3 is here. So you got the right idea. Oh, did you say positive 4.4? Oh, you positive. Okay, yeah. So positive 4 pi over 3 takes you down here, points this way. So then in this direction of positive 4 pi over 3, negative r's would be up along this ray. So that's right, negative 3.4 and positive 4 pi over 3. So all of these coordinates here all give that same point. So in polar coordinates, there are actually infinite number of ways to express any point, because we could keep adding 2 pi to any of these angles with the same r value, and we'll get back to that same point over and over again, right? But in x and y, there's only one x value and only one y value that's going to get you that point. But in polar coordinates, there's lots of ways. So we're just going to practice a little bit here. So plot each of these points in polar coordinates. 1 pi, 2, negative 2 pi over 3, and negative 3, 3 pi over 4. Find the rectangular coordinates. Remember, brain on. Think about it. Don't just automatically plug into the formula if you can avoid it. And then for this one, see if you can write the coordinates of this in 3 other ways. 3 other ways in polar coordinates. I think that is number 2. So let's talk about graphing. So, R. So what would, we saw a kind of complicated function there with E, and we looked at this one. What about something really simple like r equals sine theta? So how do we sketch this? So the way that we sketch this is we're first going to sketch this in rectangular coordinates, where we replace r with y and theta with x. So we want to first sketch y equals sine of x. Okay, and you're going to need to dust the cobwebs off here in terms of sketching cosine, sine, and variations. Okay, and variations. So this is an easy one. So let's do 2 sine x. So at least some little variation of this. Okay, 2 sine x. So can you sketch that without a calculator? So there will be a no calculator part of the exam where you have to know how to sketch basic sine, cosine, and transformations of them. So we can think about where's the midline, where's the max, where's the min, what's the period, breaking it up into 4 chunks, and making a sketch. So where's the midline of this? Sine or cosine just by themselves. The midline is 0, right? Okay. And then what's the max and the min of this? Okay, that's good. So 2 and negative 2. So there's 2 and negative 2. And the period is 2 pi. And we're going to break that up into 4 parts. Think of it part at a time. So pi over 2, pi, 3 pi over 2, 2 pi. And then as we go through those 4 parts, we can talk about where is it? Is it the midline, max, min? Okay, so at 0, where are we? Max, midline, or min? Sine starts at the midline, and the first quarter period goes to max. And then the next quarter period, it goes back to the midline, then down to the min, then back up to the midline. So here's an easy one. Sine 2x, 0 up to 2, and then at pi, it's back to 0, etc. Okay? So we're going to use this sketch to help us come up with the sketch in polar coordinates, because our x-axis here is gonna be our sweeping counterclockwise angle theta, and then the corresponding y values are gonna be our distance from the pole. So we really need some good imagination, visualization skills here, and some good covariational skills. How are quantities changing together? So we can start by looking at, as we vary theta from 0 to pi over 2, so we're looking at this part of the graph. If we vary theta from 0 to pi over 2, right here, what does r do? That's our y coordinate of this graph. So r is going to go from 0 to 2. Okay? So turn off that. Okay, so we got to think about what is the graph going to do? It's going to start at 0, and then imagine as theta increases, r is going to increase up to 2 by the time we get to pi over 2. So we're going to have that point 0, 2. We're going to start at 0, 0. So then what's going to happen? As theta increases, each time theta increases, we're going to get a little bit farther away. See what I'm doing? We're getting farther and farther away. So you can imagine here we go. So watch it. So as it changes, as theta increases, that r is moving out from 0 to 2, and you get that arc right there. Then what happens when you go back from, pi over 2 to pi? That value of this y value does what? Which is our r value. It goes from 2 back to 0. So now as the angle turns from pi over 2 to pi, imagine r coming back. So just imagine that r value getting less and less. See, it's coming down, getting closer to the pole. So watch it again. Here's pi over 2, increasing angle to pi, and the distance from the r is that point on there. So it's going to be a symmetric curve coming back the other way, or in the second quadrant. Wrong function. This one. Okay, so that was what we got before, and so now, second quadrant, as the angle increases to pi, comes down this way. Now what happens from pi to 3 pi over 2? So that's pointing into the third quadrant, but then the values are negative, right? Values are negative, so it's going to trace out back in the first quadrant. So now the positive angles are from pi to 3 pi over 2, but values of r are negative from 0 to negative 2. So it's going to trace back out in the first quadrant. See that? So it actually retraces what we already did. So it retraces what we already did. And then finally, in the fourth, pointing into the fourth quadrant from 3 pi over 2 to 2 pi, again, it's going to go from negative 2 to 0. So where's that going to be? That's going to be in the second quadrant for negative values of r if the angle theta is in the fourth quadrant. So it's going to, again, so the whole curve gets traced out. Even though the period of 2 sine x is 2 pi, the whole curve gets traced out pi over an interval of pi, and then it's just retraced from pi to pi over 2. So the question is, so what is this? Well, it sure looks like a circle. Is it a circle? So we can show that yes, it is indeed a circle, and we'll start off next time showing, we'll do the math of r sine theta and show that we're actually getting a circle. There, we'll prove it. But you have a written assignment for Wednesday, is that right? All on Parametric from the book. So you're turning in a written assignment Wednesday, and you're getting going on Clara. Just do Friday. There will be a web work on Polar as well, but that won't be due until you'll have the weekend to work on that. But I'll post it soon.